with dynamos that we will see. If I can find, yes, good. So for dynamos like Earth or numerical or experimental dynamos, it would be good if we could find upper bounds for dissipation. That would be very nice. Like for the Earth, for instance, if we could estimate what is the upper bound, we would be quite happy. And also on top of that, it would be good if we could know what is the Joule fraction of dissipation compared to viscous dissipation. Okay, these are the questions, but unfortunately, you will see that the answers are not so good. Okay, I will start to show what can be done with this upper bounds by considering a simple shear flow. No. I'm looking for yes. Okay, so it's a simple shear flow where you have two plates and the fluid in between, and you shear the fluid here. And in that context, there have been previous studies by Alboussiere, Ward, and more recently Ring and Constantine and others. And the goal was to determine an upper bound for the flow when the Reynolds number is increased. So when the flow is laminar, when below the critical Reynolds number, dissipation can be estimated very easily, u squared over h squared. And after the onset of turbulence here, what has been found is that we can have a scaling, like we can have an upper bound that can be expressed in terms of u cube over h, okay, which corresponds to the usual scaling for turbulence, Kolmogorov flow. So that's quite good. But what is derived here is really an upper bound, which means that this is an upper bound on the average, the time average dissipation, time and space average dissipation. But we are sure that we will never exceed this value because it is an upper bound. So it's not the same status as a scaling law. So sometimes people worry, why do you always want to maximize dissipation or something like that? So it's not the case, because if you take the same configuration, but instead of imposing a velocity, if you impose a force, or something, you fix a stress on top and bottom here. In fact, you will not be looking for the maximum dissipation, because the maximum dissipation will correspond to the laminar flow in that case, because the work will be the produce of the stress by velocity, and the maximum velocity you get will be the laminar flow. And in fact, you will be looking for the minimum dissipation that can be achieved by turbulence. So there's nothing special about maximizing energy. The only point is that once you determine an upper bound, you know you cannot exceed it. Whether the state of the flow will be close to that upper bound or not is a separate issue. Okay, then the point is that if you have a flow, but if that fluid is electrically conducting, if you increase the Reynolds number and if you have a small Prandtl number, at some point you will reach maybe a large magnetic Reynolds number. Then the question is, can there be a dynamo in that region? Okay, and if there is a dynamo, can we determine an upper bound after that critical number? Okay. Okay, so how does it go? This is the more recent approach by Ring and Constantine, and Hopf in the past has introduced a particular flow decomposition, so that's why his name is associated to this. So we take Navier-Stokes, and the background flow decomposition, Hopf decomposition, is that any flow, depending on x, y, z, and t, is decomposed into an axial flow along Ex, depending only on the z direction, plus a velocity, the rest depending on x, y, z, and t. And the condition we impose on phi, this mean flow, well, this background flow, which is not the mean flow, actually, we can choose any kind of background function, and that function must satisfy the boundary conditions. It's +1 at the top and -1 at the bottom. This is the only thing that is required for this background flow. And if you substitute that into Navier-Stokes, then, okay, you just substitute these terms in Navier-Stokes, and then you can dot product with V, velocity here, integrate over volume and time. So these brackets here, angular brackets here, mean integration over volume and time. So if you integrate over volume and time, there are plenty of terms that disappear, like the variation of kinetic energy. This one also disappears, and you're left with three terms here. This correlation between Vx and Vz, this term where the derivative of Vx is implied, and viscous dissipation, essentially. And if you express viscous dissipation, well, not viscous dissipation, this is the gradient of V squared. But the true viscous dissipation is gradient of U squared, the true velocity, okay? And if you apply the decomposition as well, you can see that it's made of three terms. One term is this one. Another term is the average of phi prime squared, and a third term. And if you combine, right, if you combine that with this equation here, you can get rid of this term here, right? And what you get is that dissipation is equal to the dissipation of this background flow, phi prime squared, okay, minus a bracket, okay? And so what is the game? The game is to choose phi, the profile of the background flow, to choose it such that for any kind of possible velocity V satisfying a zero boundary condition, because the boundary conditions are taken by the background flow, for any possible V, this bracket must be always positive. In that case, you have bounded dissipation by the dissipation of the background flow. Okay, that's the game. Right. How to play this game? Basically, what you want to do is have a zero background velocity profile in most of the fluid region. Okay, so in that case, if I come back, that term will be zero, which is good, because we know that the first term is positive, it's quadratic, but the second one can be any sign. So this is the annoying term, so we want to bound this one. To bound this one, we use also boundary condition because we know Vx and Vz are zero at the wall. Okay, so we will have better control of Vx and Vz near the walls. Okay, so away from the walls, we make phi prime 0. Okay, so we just have phi prime non-zero next to the boundaries. And then, right, so that's what I said. So then how do we bound this? So we use some Schwarz inequalities. So Vx can be expressed as the square root of the distance to the wall multiplied by this dvx over dz squared, which is one part of dissipation, basically, one part of gradient v squared here. You can do that for Vx, for Vz, and you can do it also near the top wall and near the bottom wall, okay? And then you can show that Vx, Vz will be less than 1/2 of the distance to the wall times the integral of grad v squared, right? So we are close to achieve something interesting, because so this distance here will be the distance delta, the thickness of the boundary layer that we have chosen. Yes?
Are you assuming something on the boundary layer structure is linear for the above the
Where?
Yeah, here, above, in the first line, first equation. No, not here. Next line. Here the Vx equal to integral -1 to z. This is some assumption, -1 to z, dz, dx, dz prime. We assume that like Vx is not function of x, for example.
Where here?
Is there some assumption here? Is this one? We assume something, or we are assuming that, yeah, no? It's assuming that Vx is 0.
Yes, of course we assume that Vx is 0 at the boundary. because this is the boundary condition for V is 0. The boundary conditions are taken by phi, the background profile. So this is why we put the gradients of phi prime next to the boundaries, so we can use this boundary condition 0 and express Vx in this way. Okay, this is how we can bound Vx and Vz compared to their gradients, basically. So then, if we do that, then we find that this term that we want to bound will be less than delta over 2 times the quadratic term, okay? And if we take delta less than 1 over Reynolds, basically, then this bracket will always be positive. Always positive. So it means then that the dissipation can be estimated as just the dissipation of the background profile, and that dissipation is twice the Reynolds number. This is dissipation over laminar dissipation. In fact, this is quadratic in terms, cubic in terms of velocity. Okay, so this is the usual way to do that. Then what is changed under dynamo action? Under dynamo action, we have Lorentz force and we have the induction equation here. Well, in fact, we can do the same thing. If we do this exactly the same thing, substitute the Hopf decomposition in both time and space average, multiply by V for the first one, and multiply by B for the second one, time and space average, like this. We add up these equations to get rid of electromotive power and power of the Lorentz forces. They disappear. And then doing the same thing, basically, we obtain that the dissipation is that of the background profile minus 2 brackets. Minus the same bracket as before. So that one we know how to make it always positive. And minus another bracket. And this is the new bracket. Okay, sorry. This I call, well, no, I don't call them. They call them the spectral condition, the fact that it's positive, because you can change the condition that this quantity is always positive. You can transform it into an eigenvalue problem, and when all the eigenvalues are positive, this will be positive. So this is the way to determine this, the bounds more precisely than just by functional analysis, as I've done just in the slide before.
But the phi just takes out the velocity bound.
Yes.
What about the magnetic bound? Is that?
Yes. There is no background profile for the magnetic field.
Right, okay.
It's just a background profile for the velocity. So B is still the full magnetic field. Full magnetic field. So now I will be concentrated on that bracket, how to make it always positive. Right? So the magnetic field doesn't vanish at the boundary. I have taken insulating boundary conditions. So it's not vanishing at the boundary. But we can show that the average at z equal plus or minus 1, top and bottom, the average of Bx, Bz, average in space, okay, and in time, that average must be 0. That can be derived from curl B equals 0, and you can derive it, or you can see it as the fact that the magnetic stress, magnetic shear, the magnetic tensor, the shear part of the magnetic tensor must be 0 at the top. Zero magnetic stress, yes, that's what I was looking for. Maxwell stress. That's, the term is Maxwell stress. So then if you use Schwarz inequalities, again, you can bound this part here with respect to the first one, but the bound is not as good as before. Here we have a delta to the power 1/2. Previously with Vx and Vz we had delta. The bound was better with velocity because both Vx and Vz were 0 at the boundary. And here only the product Bx, Bz is 0. So the bound is not as good, okay? And because the bound is not as good, we must have a smaller delta. Delta must be of order 1 over the square of magnetic Reynolds number, and dissipation then scales at the square of the magnetic Reynolds number. And this dissipation is also with respect to the viscous dissipation, laminar dissipation. So if instead of doing function, bounding the function with Schwarz inequalities, we can determine the bound using the eigenvalue problem itself. So this is the one corresponding to the hydrodynamic spectral condition, and we get something that asymptotically is Reynolds over 10 here. And for the magnetic case, we get something asymptotically which is Rn squared over 30. So if we have a unity Prandtl number, the idea is that what could happen, the dissipation divided by the laminar dissipation here, 1 initially. Yeah, actually that should be exactly 1, by the way. Then the spectral conditions, the usual hydrodynamic spectral condition tells you that dissipation is bounded by Reynolds times that dissipation. And the new spectral condition for the magnetic field tells us that it's bounded by Rn squared. So this one is U cube over H, that we can understand. It's a Kolmogorov cascade. Okay. And this one is mu squared sigma squared nu U4. If someone has an idea what it corresponds to physically, I would be interested to know. Okay, it just comes out of the analysis. And then if we have a small Prandtl number, which is interesting for some situations, with a small Prandtl number, we have the turbulent upper bound, U cube over H, for a big range of Reynolds number until the magnetic Reynolds number 1 over Pm is reached. Only after that point does the spectral condition, the magnetic spectral condition, exceed the hydrodynamic spectral condition here. So up to 1 over Prandtl, you cannot exceed the usual dissipation scaling, and after that point, it is possible that you have some higher dissipation.
So dissipation is always lower than the top curve?
Yes. Okay. Yes, because dissipation is estimated by the gradient of the phi squared, the background flow, only when both brackets are positive. Both brackets are positive only below these curves, basically. Yes. So both curves must be satisfied. Okay, so now if we just want to see what's happening in case of Rayleigh-Bénard, we can try to. Yes, no, I just forgot one point maybe. Yes. The thing is, even after that, when magnetic Reynolds number exceeds 1, even before that point, it is possible that there is dynamo action. Who knows? If there is dynamo action, we will not exceed the total dissipation, Joule plus viscous will not exceed that value. But the thing is, we don't have much control over the ratio between Joule dissipation and viscous dissipation. I don't know. The only thing is that the only thing we know is that some dissipation will be needed to produce a magnetic Reynolds number of order 1. Okay, so if we look at Rayleigh-Bénard now, we can maybe ask the same question. I've put it in a different way here with the Nusselt number, the heat flux, versus the Rayleigh number. When we increase the Rayleigh number, well, for some time the system is stable, and after some critical value, the Nusselt number increases as the consequence of convection and turbulence. And then it might be also possible that the magnetic Reynolds number becomes large enough to produce dynamo action. And what's going to happen And in that case, we can, right. I will first, show how the Hopf-Doring-Constantine method works for convection. So we start with Navier-Stokes and the temperature equation in the Boussinesq approximation. Here, this is the Boussinesq approximation. And we can write the background temperature again with a background profile, tau of z, plus disturbances. And the background profile of temperature takes the boundary conditions. Here I have chosen 1/2 at the bottom and minus 1/2 at the top for the dimensionless temperature. So the thing that is done is to dot product Navier-Stokes with velocity, integrate over volume and time. Okay, you get the work of buoyancy is absorbed by dissipation, and you take the product of thermal equation by theta, and you get a second equation. Okay, and these two equations will be used later. Now we need to express the heat flow, Nusselt, and the heat flow, it can be shown that if you integrate the dot product of temperature T with the thermal equation, you get that the Nusselt can be expressed as the product of grad T squared. Grad T squared integrated over the volume. Okay. Now if you substitute the decomposition, this has 3 terms again. And when you use the two equations on the previous slide here, you can get rid of this one and substitute the other one, and you get that Nusselt is tau prime squared, okay, minus a bracket. And again, as usual, we want to make sure that that bracket will be positive for any possible choice of u and theta. Okay. These two terms are okay, they are quadratic, always positive, but this term can be positive or negative, so we want to bound this one, uz tau prime minus 1 theta. So well, the usual game tells us that what we want to do is to have tau prime minus 1 equal to 0 in most of the flow, and confine its variations just in boundary layers. Right? So this leads to a very weird temperature profile, yeah? Because if we want to have tau prime equal 1 in the bulk of the flow, this is tau prime equal 1 here. But this is not going to meet meet the boundary conditions. Okay, because the boundary conditions are that it's hot at the bottom and cold at the top. So we need to have thin boundary layers where the temperature profile goes back to the correct boundary condition. Okay, and in these boundary layers, and because of the boundary condition that theta is 0 and u is 0, we have a good control of u and theta with respect to the gradient of u squared and the gradient of theta squared. Same idea. So if you use, again, playing with Schwarz inequality and choosing delta is 1 over the square root of Rayleigh, we can see that the spectral condition is satisfied. The bracket is always positive in that case. And the flux can be bounded as something proportional to the square root of Rayleigh. Okay, this is in the book of Doring and Gibbon. Very good book, by the way. So in that case, the result is that increase of Nusselt with Rayleigh number can be bounded by Rayleigh to the power 1/2. Okay, we can discuss whether this is a good bound or not, but some people are still talking about the ultimate regime for convection, which might be also Rayleigh to the power 1/2. Yes.
Sorry, so going back to the previous profile you drew, with the linear tool, that's the temperature?
This is the background temperature profile.
Yeah. So, I mean, if you're doing something, if you do the Buster type approach, I thought the internal part of temperature was uniform, was constant.
So
you just get thermal downgrades once more. The temperature in the middle was, I thought was
Well, the Alboussiere approach I'm less familiar with because it's not well.
I mean, I may be wrong.
Well, I know that in this approach, this is the background profile that is needed. Yes. Yes.
And if you solve the spectral constraint, do you find also this kind of profile, or maybe you would recover the Alboussiere profile?
No. Well, in fact, you have first to choose the profile, and then you solve the eigenvalue problem.
When you try to calculate the optimal Joule.
Yes, the optimal profile.
Yeah.
Yeah. In fact, there are even some more complicated optimal profiles. Like this, instead of being a straight line, it's a sort of log function or whatever.
They're always like that.
Yes. Yes. Yeah. Yeah. Yes. Okay. Right. Okay, that I said already. So what's happening if there is dynamo action? What's happening? Well, in fact, nothing basically, because if you consider the induction equation on top of that, you will add kinetic and magnetic energy equations that will cancel electromagnetic power and power of the Lorentz forces, and the bound will always be the same. Right. Well, that's quite. I think you can understand that from the fact that if there is dynamo action, we may expect that the flux will be less than what it is without dynamo action. But there is still the possibility that dynamo action doesn't happen, so the bound will not know. The bound will still consider the worst possibility, and it will be the same scaling, right? Then this was the heat flux. Then dissipation. We need to estimate dissipation. The heat flux is the convective part of the heat flux plus the conductive part of the heat flux. And if you integrate that over the thickness of the layer, you can write it this way. And if you take the dot product of Navier-Stokes with the velocity, you get this balance of energy. And combining both equations, we get that the total dissipation, right, will be this dissipation parameter here, right, alpha GH over Cp, multiplied by the difference between the actual flux minus the conduction flux, right? So this is the way of getting dissipation once you have the heat flux. And if you take that dissipation and you translate it into a magnetic Reynolds number, okay, you find that magnetic Reynolds number cannot be of order unity if the Rayleigh number is less than the Roberts number to the power minus 4/3. Okay, so that you have some idea of when dynamo action can take place in that Rayleigh axis here. Of course, it will probably never take place before, and perhaps take place after that value. Right. Okay, so conclusions. Conclusions. Some bounds can be obtained. Okay. But sometimes it is hard to see what they mean, right? That's not very positive statement, but it's how it is for the moment. And perspectives is that there are two things I think that would be interesting. One is that the effect of rotation has not been captured, basically, for convective flows. And it would be, I think, very interesting to have it, because it's interesting in many physical situations. And the effect of compressibility is very difficult to handle, because this approach that was working for the Alboussinesque approximation is really unphysical. I mean, you have quantities like T multiplied by the thermal equations. You have so the thermal energy is sort of T squared, which is not physical at all. So as soon as you want to put some more physical model, even an inelastic model, then the same method cannot apply at all. Okay, so thank you for your attention.
Okay, question.
So if you stick in real numbers for any system, Earth or whatever, so what
For the Earth, I would think so, yeah, because really 1/2 compared to really 1/3, for instance. Yeah, I think so.
Three
Yes.
factors at the order of 100, if I remember correctly.
Also, yes, but that, especially for the Earth, I think taking into account rotation would be very interesting. At the moment, it's not.
No other questions?
I have two questions.
Okay.
One is related to the unbelief question. So, as far as I know, so the profile, temperature profile should be very flat.
Yes, 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 yes.
Then you mean so some counter gradient occurs?
Yes. Well, this is not the mean temperature profile. This is just the background profile for this analysis, which for this type of analysis gives the lowest possible upper bound.
Lowest, okay.
We want the lowest possible upper bound, okay? And it turns out that for this analysis, this is what we need to take.
Okay. Okay. The second question.
Yes.
So, as you know, in the case of wall tablets,
Yeah.
we have very definite law of von Karman's law.
Yes,
of
yes.
Ball
Yeah. Ball law, yes, yes,
So, and also in the case of current quick flow, as you showed.
yes. Also, yes.
We can integrate the equations. Then, so I just wondered, in your profile, satisfied with such a log law?
Well, in fact, a lot of people like
Again, the same answer.
yeah, during Constantine, they've been trying to find out whether by improving the method, the ideal background profile would come closer to the log law, for instance, but it doesn't. In fact, it doesn't. It's not. I don't know exactly what it means, but you cannot recover the log law from this method.
Okay, so it's quick, yes.
When you were pointing in the first part in the case of shear flow,
Yeah.
you seem to make a difference between Bx and By. The relation you were showing was Bx, Bz everywhere. There is no constraint in By.
By doesn't appear in the equation.
So we don't care that it makes sense.
Yes. Yeah, but you will have the same. By, Bz average will be 0, but it's useless. Well, perhaps not.
Okay.